So next to the fun part, and that's actually building our deep learning model. Essentially, a deep learning model can just be thought of as a multi-layer neural network where we have an input layer, a hidden layer or hidden layers, and also an output layer. There are a few main parameters which we use to configure the architecture of this model. The first is n layers, or the number of layers, and this is how many hidden layers are in the network. So in this image here, n layers would be 2, because there are 2 hidden layers. If you set the number of hidden layers to be quite high, the model can learn complex patterns, but it can also overfit the data, and training the model can be considerably slower. If you set it too low, you get a simpler, faster model, but it may miss subtle patterns. The next is the units, which give the number of neurons in each layer. So in this case, each layer has 4 units. If you increase the number of units, similar to the number of layers, you get better capacity, can learn more complex patterns, but the model can be heavier and slower. And if you set it low, you get a lighter model, so it's quicker to train, but it can underfit the data, quite similar to the number of layers. Next is the dropout rate, and this is used to fight overfitting, and it is the percentage of neurons that are randomly turned off during training. So you can imagine here, if we set the dropout rate to 25%, then one of these neurons will be wiped out during training. So this essentially reduces the number of units and fights overfitting. If you set it too high, you might end up with a too simple model. You're taking out too many neurons. And if you set it too low, it may overfit the data. The last parameter, and there are more, but for this project, we just focus on 4, is the learning rate. So the learning rate essentially configures the size of each step for optimizing our model. If you set it quite high, during the training process, large steps might be taken to try to optimize the model, but you might actually miss the optimal solution. You might go over it. If you set it too low, however, you might end up being too careful, and you often require more training iterations to optimize your model. So before building this model, we don't want to come in with like a bias and be like, okay, we want the number of layers to be 4, we want the learning rate to be 0.2, we want the number of units to be 50, and so on. We want the computer to figure out what are the best hyperparameters for our model. And for that, we use a optimization library called OpTuner, which essentially samples different hyperparameters. So it might train one model with the number of layers set to 4, another model with the number of layers set to 2. And essentially, it samples these different hyperparameters and it returns the model with the hyperparameters that gave us the best performance. In order to use this library, we make a function called buildModel. We define our 4 hyperparameters and we tell it where to sample from. So we say the number of layers should be an integer between 1 and 4. So it can try either 1 layer, 2 layers, 3 layers, or 4 layers. The dropout rate, which can be a float between 0 and 0.5. That can only be 32, 64, 128, 256, and 512. And lastly, the learning rate, which can only be between 1 times 10 to the minus 5 and 1 times 10 to the minus 1. We then build our model based on what's selected here. So we add our input layer and hidden layer. We then add n layers more hidden layers. And lastly, we add an output layer. We then compile the model. And in this case, we're looking to optimize accuracy. And then lastly, we return the model. We then build another function that iterates through these different models that are built in our build model function and finds the model that gives us the best accuracy in the validation set. We then make an OpTuner study and we feed in this objective function where we're iterating over these different models with different hyperparameters, and we try to find the model that gives us the best performance. So running this code gives us the following printout. Looks quite messy here. However, in the article, I extracted what was printed and put it in a table, so it's more, I guess, presentable. And we can see here the different trials, the number of layers that were used in each trial, the number of units, the dropout rate, the learning rate, so essentially our 4 hyperparameters, which we explained earlier, and also the returned validation accuracy. Looking through each of these trials, we see that trial 9 resulted in the best accuracy of 99.8%, which is amazing. Just another observation, we can see just how much the values of our hyperparameters affect our model performance. For example, here in trial 2, we got an accuracy of 4.4%. And as we sample different hyperparameters, we managed to get up to 99.8%. So these hyperparameters are really crucial in building a high-performing model. In the article, I give a brief overview of how the hyperparameters are sampled. So they aren't just randomly sampled. There is something called a tree-structured Parson estimator, which, to be honest, I haven't delved too much into. But essentially, it uses the first 10 trials to identify where to sample from next. So the first 10 trials are in the startup phase, and then you have what's called the guided phase, where the algorithm kicks in, looking at the first 10 trials, and tries to sample with a bit more sophistication. So going back into our code here, we can then extract our best hyperparameters and print them here. So here we can see the number of layers is 3, the dropout rate, the units, and the learning rate. We then need to rebuild the model using these best hyperparameters that were identified. And that's done using the following code. I don't want to go into too much detail into this, as I plan to build a whole series just on deep learning. So we make another function called best model, and quite similar to before, but this time we're using the best hyperparameters to build the model. So we set the number of units to be the units identified here, which is 128. We set the dropout rate, which is identified here, the number of hidden layers, and so on and so forth. Once we have defined our model, we then need to train it on all of our training data. So here we set the number of iterations to be 15, the validation split to be 0.1. So we're still taking 10% of the training data to check the accuracy on each iteration. And we also set what's called early stopping. So if the model isn't improving after a set amount of iterations, then it stops. This can take quite some time to run. So I set the number of epochs to 15 just to save time. However, usually you would want it much more than that, especially, if you're building a model that's going to be used in hospitals or in the NHS. You want a lot of computational power to ensure you're using the best possible model. So if you run this, we can see each of our iterations, and we can see how our validation accuracy is increasing for every iteration. So it starts at 0.7126, big jump to 0.9328, and then incremental increases all the way to 0.9983.